Good evening, everyone. Uh, Thank you very much for listening to my lecture today. I'm just repeating or summarizing most of what the this lecture is all about. And again, it's about theoretical and experimental studies on partial oxidation of methane to methanol in water splitting using transition metal oxide anions. Uh, we did this work in a collaboration with the Billings Lab at Hopkins University, and we will talk much about catalysis, how we can catalyze reactions, what is the best circumstances for having a good catalyst, what are the factors that determine the viability of a catalytic cycle, and stuff like that. So, several factors determine the viability of a catalytic cycle, and the most important ones are as follows. The recovery of the catalyst and at the end of the chemical reaction is one of them. The completion time, the yield, all of these factors are affecting how good your catalyst is. But before that, what is catalysis? Well, catalysis is the field of chemistry focusing on the acceleration of chemical transformation facilitated by a mediating molecule, which is the catalyst. Like I said, the factors we consider when choosing our catalyst is the recovery. The recovery means when the catalyst is, you know, uh, speeding up the reaction, interfering with the reactants interactions. We want finally to get it back to want to recover this. So we care much about the recovery of the catalyst. We also care about the completion time, how much time that the catalyst takes to finalize this job. So the shorter, the better. And we want the job to be done in a very short amount of time with a high yield. So the yield is pretty important as well. You want to recover your catalyst after the catalysis process happens. You want to complete this in a good amount of time, and you want finally to have a high yield. Any catalyst that have these three factors combined are called good catalyst, and it's going to be approved for catalysis. This figure represents the energy diagram of a chemical reaction. The uncatalyzed reaction is shown by the bold black line, as you see here. Let me see. Let me point it out to the black line. This black line is the uncatalyzed reaction, and this red lines and the catalyzed reaction. So what happens is the catalyst job is to convert or to reduce the energy barrier by going through transition states or multiple transition states with lower energy barriers. So what exactly happening is instead of this high energy barrier with the catalyst, that energy barrier is divided into multiple small energy barriers, and this is going to be effective in finalizing the process or the chemical process, so we can go from A as reactants to B as product smoothly and effectively. It's worth saying as well that you have to sometimes, or a lot of reactions, if you don't have the catalyst, the reaction wouldn't go from here to here. So a lot of times the reaction would like stops in the middle, and without the catalyst, it's not gonna happen. So the catalyst function is not only speeding up the chemical reaction, it is necessary for the reaction to complete and to happen. Uh, for this project, we are studying mainly methane to methanol conversion, and we will briefly talk about the importance of each one of these compounds. Methane, methanol, and formaldehyde. The cycle happens, or just the expectations for the chemical reaction we're focusing on is methane is going to methanol, and methanol is going to formaldehyde. So we are studying methane to methanol conversion and methanol to formaldehyde conversion, and we will shed the light on what is called the holy grails of chemistry, which is methane to methanol conversion, and we will focus on this because this is a very important topic in the catalysis world. Going from methane to methanol, since the reaction wouldn't stop at methanol, and we will know why this is happening, what exactly the problem is, and so on and so forth. So methanol commonly used as solvent in industry. Methane is abundant gas, holds significant promise as a resource for energy and chemical production, and it's also comprising or just forming around 70 to 90% of the natural gas. It's considered transitional fuel that contributes to the current dependence on finite crude oil reserves. Despite its potential, methane is identified as a greenhouse gas, and this is the main problem of it. So methane has, like, it's a double-edged sword. It's good since it's a source of energy or a source of natural gas, or just it's in the composition of the natural gas, but at the same time it's a greenhouse gas, and the complication that happens by having gases as a greenhouse gas is multiple, and we will go over this as well. So despite its potential, methane is identified as a greenhouse gas, with its release adversely impacting the global energy balance and contributing to climate change. The global board, one of the things that caused by methane is, since it's a greenhouse gas, is what is called global warming. So it causes global warming with what, and that leads to flooding, for flooding, and affecting the agriculture, affecting the environment, affecting crops, and so on and so forth. And it has complication with the weather and the climate. So it's worth telling that the global warming of potential of methane is 25 times greater than that of carbon dioxide over a century, and this is a threat. This is not good. Underscore the environmental concern associated with its emission. Methanol is known as wood spirit as well. It can be used as an energy carrier and source of energy. There is a high demand for methanol production in the world, especially that it has already reached like 75 million metric tons in 2015 only. Methanol is advantageous for transportation because it is liquid under ambient conditions. So much attention to methanol production is really considered, and this allowing it to be transported in conventional tankers vehicles. This stands in contrast to methane, which requires energy intensive liquefaction techniques for transportations, which are known as LNG, liquefaction techniques for transportation. So methanol has a competitive thermal content and can provide a comparable amount of energy when used as fuel. That's why it gains much attention, making it a viable option. Methanol is also a feedstock to produce chemicals such as dimethyl ether, formaldehyde that we're going to be talking about, and propylene. So these three compounds are under much attention and interest, and we will study them one by one. So, like I said, that summarize what I just said. Summarize the importance and the significance of each one of these compounds separately. So, a greenhouse gas. The greenhouse gas, it's any gas. So we know methane is a greenhouse gas, and for the definition of this, a greenhouse gas is any gas that has the property of absorbing infrared radiation emitted from Earth's surface and re-radiate this back to Earth's surface, thus contributing to uh, global warming, um, elevation of temperature on Earth, flooding, melting of ice in the icy places, and you know Environmental balance will be affected and messed up because of this. So many bad problems happens because of this. So it really needs to be taken care of. Methane as a compound. Methane is the second most important greenhouse gas, and methane can be converted to so many molecules and so many processes. The methane industry is huge, and it has so many good impacts on life, but at the same time, methane has bad impacts on life. So we need to monitor this environmentally. We need to take care of this. We need to, uh, make methane at the standards, or know how to control methane production and how to deal with it. The most important part here is that methane can be converted to chemicals through two ways. One is called the indirect route, and it's called syngas based route. And for those of you who don't know what syngas is a combination of carbon monoxide and hydrogen. And the other route is called direct route, not syngas based route. So these two routes are the ones you can go from methane to methanol through. But the point is, the indirect routes are the most common routes and the plausible possible one. The other route, which is the direct routes, full of troubles because the methanol we are producing, or just, the oxidation that happens to methane, it's not easy to control. Since the carbon hydrogen bond in methane is strong and it needs, tremendous amount of energy to dissociate it. So direct oxidation till today is still, it is called one of the holy grails of chemistry, or the holy grails of chemistry. And it's not easy as it looks to directly oxidize methane. So much attention has been paid to this process, definitely because of the usage of this route, and at the same time because the difficulty of stopping at methanol without suffering from the consequences of overoxidation of methanol that leads to, formaldehyde and formic acid and so on and so forth. So till now, this direct route, there is no low cost effective way till today to go directly from methane to methanol without suffering from the partial oxidation, or the oxidation of methanol, which is a bad thing. And so the partial oxidation is like the predominant thing in the direct oxidation process, and still work needs to be done to be able to control this. On the other hand, the indirect route, which is the most common route industrially, and people are going for it, that route, yes, it's good, but it's go through multiple processes, and definitely that brings more cost. So, the necessity for a direct route to be able to do it became more demanding, and there is a high demand for this route. So, and research and scientists all over the world and given much attention to the direct route, to and choosing, or just selecting multiple catalysts so they can successfully do this. Anyway, so the bottom line here, we are going from methane to those chemicals, and specifically partial oxidation to methanol and formaldehyde through the direct route is one of the most important problems that the world is paying much attention to. And this representation will introduce our approach to this, how we can go from methane to methanol directly, what is the catalyst that we are bringing up or coming up with, so that can help us with that. So this slide summarizes the direct route and the indirect route. The direct route, which is a non-syngas path, there is no carbon dioxide and H2O amongst the steps. That step does not include syngas stages, but this route is what's called indirect route. It happens through multiple stages, and it has the carbon monoxide and hydrogen, which is called the syngas based route. Our focus now, or the world's focus now, is on this route to improve it and to reach a catalyst that stops at the methanol and does not overoxidize to formaldehyde. So this is the whole path. Methane will be oxidized to methanol, and this is the direct path. Unfortunately, the direct path will not be completely stopping here. It will undergo further oxidation to formaldehyde, which can be further oxidized to formic acid, and finally, this further oxidation can get us the H2O and CO2 finally. So, whether, like, oxidizing agents are various, and our main goal as researchers and chemists interested in catalytic chemistry is to find the catalyst that can get me from methane to methanol, a catalyst with low energy barrier going from methane to methanol, and at the same times, that catalyst we are we would be very fortunate if we have the catalyst with a high energy barrier going from methanol to formaldehyde. That high energy barrier makes the reaction stops at methanol. If we found the catalyst going from methane to methanol with a low energy barrier, that would make us happy with the transformation process. And if we found the catalyst, that same catalyst that would be with a high energy barrier from methanol to formaldehyde that makes the reaction stops here, we would be happier with that catalyst. So lots of research has been done on this, and hopefully we can, adopt a catalyst then get us this. So our approach will be nickel oxide anions and palladium oxide anions, and we will go over this quickly. I know you guys, you are not merely experts in the field, so I'm not gonna go into the every fine details, but instead I will go over the whole background about. I want you to have a better background about this topic, so you have more understanding how this works and how could you improve it and how could you go from a methane to methanol, or how could you think about this? How could you let me put it this way? How do you think about it? How do you go to methane to methanol? How could you do this? How could you theoretically come up with the suggested or expect, or your approach to the catalyst then that can get you this job? That B has some questions. Why methane to methanol? Why methane to methanol conversion considered an environmental problematic issue and global issue? And finally, not finally, sorry, why methanol to formaldehyde? Why do we care about this as well? And why transition metal oxides can be used as catalysts? Okay, let's we I think we went over this. So methane to methanol. According to the chemical properties, generation of methanol has various applications. So far, there is no practical, low-cost way of direct methane to methanol conversions, which is considered the holy grails of catalysis. So in catalytic chemistry, so we want to come up with suggestions for this. From an environmental perspective, we are trying to reduce the harmful effects of methane as a greenhouse gas, reduce the global warming by methane, which is 25 times greater than CO2, which means we are trying to regulate and control the methane production. So, why methane with methanol is a problematic environmental issue? So, like we said, there is no low cost process so far. Uh, we are suffering from the low selectivity of the direct path because we are not stopping at methanol. The conversion rate is not that satisfying. So for that, we are coming up with or we are studying the negatively charged metal oxide anions catalysts, and we are trying the cyclic peptide ligands as well to improve those catalysts in the future, as a future project for us. So for this, in order for you guys to dig more and understand more the significance of transition metal oxides and their complexes in the methane chemistry, I urge you to review article, transition metal oxide complexes as molecular catalysts for selective methane to methanol transformations. Any prospects, or it's a time to retire. That review article really shed light on how important the metal oxides anions in the methane industry or the methane chemistry, and it focuses and praises the efficacy till now or till today to the metal oxides as candidates for methane chemistry or methanol chemistry. So I urge you guys to look at it and read it, and it's really important to have this background about methane to methanol chemistry. Uh, the bottom line: metal oxides exhibit distinctive properties that facilitate various significance reactions. So why you say that? Why this is happening? The presence that makes them, outstanding or much better than metal oxide cations, because the presence of oxide anions due to their larger size compared to those of cations gives them a nucleophilic character to the catalyst, and that will, by its role, enhance the ability of those species to attack the methane or react with it or interact with it. And that would increase the rate of the reaction, and that would finally let us see or get us the product that we seek from this chemistry. This characteristic potentially enhance catalyst reactivity and selectivity in comparison to atomic catalysis. My motivation with this article called, or just the title, Methane to Methanol Conversion Facilitated by Anionic Transition Metal Centers. And they try in this iron, nickel, palladium, and platinum. And we go from there. And we used our nickel oxide anions as catalyst, and we studied them in addition to the palladium as well, oxides. For the computational methods, I know it's I just summarized the computational methods used for this. For the quantum calculations, we were doing them using the Gaussian 16. For the method, this was called MN15. This is MN15, B3LYP, and so on. But, for those who are mainly interested in theoretical chemistry, it's important to choose the appropriate basis set and the appropriate method. The appropriate method and the appropriate basis set to handle your calculations. And each method and each basis set are mainly specified and for a bunch of, or associated or are mainly for specific calculation of specific molecules or specific species and so on. So it's not random to choose anything with anything. You need to do your lit review. You need to have your understanding to choose the best business set and the best method for the calculation that you want to handle. And all the calculations were done using HPC, supercomputer. This is a tiny the results. There's a tiny adjustment here. The calculations were done using easily supercomputer. Sorry for this. So initially, methane. This is the bottom line of the process, how to go to methane to methanol. And in this, we do our calculation for each transition state and intermediate along the road to finally get to the methanol that we wanted. And finally, we recover the nickel anion. Eh, it's for you. I know it's a little bit, you know, difficult to understand what's going on here, but we are just explaining through this, and each one of these steps are done on supercomputer, and we use the structure, the coordinates of each step of each structure of these, and we run these calculations on the supercomputer to know exactly if it's possible or not. So each one of these steps is proven in calculations. We are not doing them randomly. So, and it's taken few months, definitely, or just maybe at least, I don't know, but I don't think this work is gonna be done in less than 2 to 3 months to finalize this. So it's really takes time to finalize, and it really takes time to prove your theory, or prove, or to match up, or to go along with the experimental results, and to prove them right by the theoretical results as well. So initially, methane transfers hydrogen atoms. So you have this nickel oxide anion. It is gonna react either from the terminus oxygen or from the nickel ion side. So either from the nickel or the oxygen. So these two approaches, these two routes are, this is all about. Either you will have the hydrogen approaches, the oxygen, or the reaction starts by the interaction between the oxygen of the nickel oxide or the nickel of the nickel oxide with one of the hydrogens of the methane, until you finally go to the methanol. So this is the bottom line of it. And this is in details the how the reaction would happen, how the the mechanism by which the methane is completely transformed to methanol, how this happened, what are the transition state behind this. So this route is going through 1, 2, 3 transition states, and these are the intermediates amongst these transition state to get you finally the methanol. We did this with nickel oxide, the energy diagram for it. And it's worth knowing that each intermediates to intermediates, there is a transition state in between. And we calculate these, all those, there is a way to do the transition state calculations, and there's a way to know the energy of each intermediate. We do this through the supercomputer, and our template will be adjusted according to what we want it, to calculate. Whether if you want this, so your template or your coordinates should be these two. If you are if your hypothesis say that this could be a transition state, or you are assuming, or you are given a theoretical assumption that the reaction will start by this hydrogen to sorry, by this reaction by this hydrogen to finally attach to the nickel through this transition state to give me this intermediate, and then the oxygen will attract the hydrogen on that nickel, and so this transition state will be a bearing. And finally, you have this uh, 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 nickel oxide. You want it out. You want this nickel out. So that happened through another transition state was here. These two bonds will be stretching in order for this nickel to be out. So you are left with the methanol. So all those, this is a transition state. This is a transition state. This is a transition state. So all these transition, this is a transition state. This is a transition. This is a transition state. So all these transition states are calculated and known, and your data will support this. The calculations that you are and the file that you are having out of the supercomputer, and you view them with the Avogadro software, you will see that. So definitely, you will not fully understand this until you do it yourself, the way I did it. But all these things are, you can master them if you are doing them all the time. You pass and fail and send the job to the supercomputer. It comes to you either failed or successful or whatever, and then you will master these things. The other route with palladium oxide, you can see it now. Palladium oxide can do the exact same job, and we calculate the transition state and the intermediates for palladium oxide route. And finally, we have the energy diagram to compare between which one is better, the nickel oxide anion or the palladium oxide anion. And it was proven that the nickel oxide anion is going through lower energy barrier than the palladium oxide anions. And that's why nickel oxide, we paid much attention to it, to use it as our catalyst under study. Uh, and we did the calculation for both, as like I said. So going from methanol to formaldehyde, like I said, you want to know, or you are doing this to calculate the energy barrier by going from methanol to formaldehyde. And in order to do that, you will do the exact same thing. But now your starting material is methanol, and you will end up with formaldehyde. So you are trying to calculate the energy barrier going from methanol to formaldehyde, hoping that the energy barrier is higher than expected or high, so that reaction most likely, or that catalyst most likely will be good to use as methane to methanol conversion. So we are hoping that this is going to happen. So we come up with scenarios that, or you calculated the transition state intermediates for all the scenarios where the methanol can be converted to formaldehyde. On paper, we do them, and we go one by one, and we calculate the energy state, the transition state, the energy, sorry, for each one of these compound with a transition state or an intermediate. And then we will view them and we will suggest them. We not suggest, we will show them, show the whole route, whole scenario. How could we go from methanol to formaldehyde? Is it possible, that route? If this scenario possible or not? You do this on paper, you run your calculations, and then your calculations will guide you whether this path can happen or not. And definitely when you do this as well, you have your own expectation, and that comes by what's called chemical tuition. Chemical tuition, you can expect whether this route is going to happen or not, even if you didn't do the the calculation, or you didn't use the supercomputer for this. Your chemical tuition will help you, and when the calculations or the job stops and fails on the supercomputer, at that point when when you view your compounds or the structures, you're kind of be aware of why this is failing, why this route is not happening, and according, or just your expertise with chemistry and theoretical chemistry and energy and training and practicing and this, you kind of have this sense of whether this reaction is happening, is going to happen or not, and if it's not happening, why. You will by time master and have this knowledge. And you didn't have to know the reason for everything, definitely, but sometimes you know the reason. Sometimes you know the reasons, and a lot of times you know why this reaction is not happening. So this scenario one, and this is the energy diagram for it. Scenario two, definitely it's like reaction mechanisms. It's you can figure it out yourself. It's worth just telling that the green balls are the nickel, the oxygen are the red ones, these are the carbon, and these are the hydrogens. Okay, and this is scenario 3, the energy diagram for it. The scenario 4, the energy diagram for it. Scenario 5, the energy diagram for it. And scenario 6, the energy diagram for it. And this is the comparison between all the scenarios of methanol to formaldehyde conversion and the energy barrier to each one of these scenarios. Uh, I think so many slides. You can even go from methanol to methanediol, and this is the path for it. I don't want to take much of your time on this. I don't want to make this very longer. And as well, we can use our calculations to predict or to help us with water splitting. This is a few slides about that. And I had a question today about the combination or the uh, what is it called? The how the experimentalists and the theorists are collaborating. So this is an example of how we collaborate, guys. So with our calculations, we can calculate the binding energy, like in this diagram or this figure specifically. So the theory part or the theoretical chemist will calculate the energy, and then the experimentalist will do this as well. And whenever we are going along with each other, we're close to each other. So this is proves our theory and our approach that we are doing this right. So many details about it. I don't want to go into much details. I know it's kind of, in order to go about over every single detail is going to take so much time. But the bottom line, you do water splitting as a source of hydrogen to use it as a fuel. So molybdenum oxide, we tried molybdenum oxide 3 as the metal oxide 9. So MOO3 was the one we studied, and this is the results for it. And this is the theoretical result, and or here the theoretical approach and the experimental approach, and thankfully we are very close to each other. So whenever we are close to the experimentalist results, that gives us confidence to our calculations and gives the experimentalist a confidence of his results as well. And this is kind of a whole a diagram, or just this slide summarizes how we go from molybdenum metal, a rod, through laser, or, and we can convert it to molybdenum oxide 1, 2, or 3. We can control this, and then the two compounds that can generate out of the reaction of molybdenum trioxide with water, and these are the transition state intermediates for this. And this is as well, since we knew that this form would be the most preferable one, we just calculated the energy for how this is going to happen, like in that structure, in which form it would be, or the energy that will be accompanied with each one of these, or the structure of this one, how exactly it would be like this, or the OHs would be like this, or like this, or like this. So we calculate the energy of each one of these structures, and we know which one of them is more stable and which one of them is less stable. And there's so much things we can do with our collaboration with the experimentalist and theorist, and so much things with the experimentalist can gain out of their collaboration with the theorist. A conclusion, there is a global necessity for methane to methanol conversion, and this has a good impact on the environment and the chemical industry. And uh, you know methane to methanol still now till now is a puzzle, how to directly oxidize methane to methanol. How could we increase the yield for this, and how could we find a good catalyst for this? Methanol oxidation has been a theoretically proven possible process to produce one of the world's important chemicals. It's called formaldehyde. Both methane to methanol and methanol to formaldehyde conversion were done experimentally and theoretically using nickel oxide anions in the gas phase. This was through our collaboration with Hopkins University and Dr. Bowen's lab, and the possibility of oxidizing both methane and methanol through nickel oxide anions confirms that transition metal oxide anions are worth studying in the future as promising candidates for catalysis. With that being said, I just would like to shed light on our future work that we want to do at Tuskegee. We want to do the calculation considering metal oxide ions of the first, second, third, other, uh, you know, other types of or other uh, transition metal oxide anions. We will use this and we will do our calculation with it. And we can add more ligands as well to the current catalyst, and we can synthesize these complexes with this transition metal oxides and use them as catalysts. And we can evaluate their behavior by calculating the energy barrier between each transition state and intermediate. This is the publication supporting. I was involved in them supporting my results, or just and I was lucky enough to working with very incredible people that helped us, know stuff about a field of chemistry that I has never been involved in since I work with those incredible people. I mentioned them. They are in the publication list now. And thank you so much, guys. First of all, I just sorry. Finally, I would like to let you know that I am posting the questions. You're gonna find them on as a form, and you will get an email today. And thank you very much for watching. And please stay safe and have you all a good night. Thank you.